So today's warm-up question probably seems a little easy. I guess we'll just see what you guys said though. It says sit as still as possible and then turn and look at your neighbor. How fast are they moving right now? Anybody want to share what they put for how fast their neighbor is moving? They aren't, okay? That is a good answer. Anybody have a different answer than Chase? Yes. Constant speed? How fast?
0 miles per hour.
Okay, so same thing he said. 0, not moving. Constant, but is constantly not moving, sure. Anybody have a different answer? No one has a different answer. Okay, that's fine.
Moving at 1 mile per hour.
Okay, so we're going to talk about other ways that you could answer this question when we talk about relative velocity today. Your homework assignment, and really you're going to have a fair portion of the class period to work on it. It's in My Open Math on relative velocity. Other than that, if you guys haven't been paying attention, your test is on the 15th. Today is the 12th. That means your test is in 3 days from today. Tomorrow you will be taking a quiz. It's basically going to give you an idea of how you might do on that test because the quiz is going to cover everything in the unit. We will go over that quiz on Wednesday, and then on Thursday you'll take your test. Okay, so you do have a quiz tomorrow, and you have a test on Thursday of this week, so those are definitely things that you need to be keeping in the back of your mind as you're studying, and that unit summary is a great tool for studying. But let's go ahead and talk about the warm-up because your answer to this question depends on your frame of reference, and we're going to talk about what that means in a second. So most of you said this, you're not moving compared to your neighbor because from your perspective, yeah, sure, you're not moving anywhere, neither are they. However, you could have told me that they were moving at 750 miles per hour because that's how fast the Earth is rotating, and technically you're on the Earth, and therefore you are moving at that speed as well if your frame of reference is from outside of Earth looking at the Earth. You're also moving at 66,000 miles per hour because that's how fast the Earth is moving around the sun as it revolves. Okay, so you could have said that. Again, different frame of reference. Not only that, but you're also moving at 483,000 miles per hour because the whole solar system is orbiting around the center of the Milky Way galaxy. So if we zoom out a little bit further, you could have answered that a little bit differently. Or even this. Our entire galaxy is moving toward Andromeda at 1.3 million miles per hour. So different ways to answer the same question. Technically, you're in the galaxy, so technically you are also moving toward Andromeda at 1.3 million miles per hour. Yes. It is another galaxy. What? All right, so yes, if you're more interested in the space aspect of this, sign up for astronomy. All right, but anyway, we're not going to get into that part, but I did want to point out to you that your answer depends on your frame of reference. And this video clip, this TED Ed, is going to go into that question a little bit more. And I think it's pretty entertaining. It's a cute one. It's not that long. So please give your attention to my video clip at the front, and then we'll talk more about relative velocity after this clip is over.
How fast are you moving right now? That seems like an easy question. The first tempting answer is, I'm not moving. Upon further reflection, you realize that maybe the Earth's motion counts. So a second tempting answer is 19 miles per second around the sun. But then you recall learning that the sun moves around the center of the Milky Way galaxy, and the Milky Way moves within the local group of galaxies. And the local group moves within the Virgo cluster. And the Virgo cluster moves within... How fast are you moving is not an easy question. When mission control tells astronauts how fast they're going, there is always an assumed standard of rest. At the start of the voyage, speeds are given relative to the launch pad. But later, when the launch pad is just one more arbitrary place down there on Earth's spinning surface, speeds are given relative to the idealized, non-spinning, pinpoint center of Earth. On their way to the moon, Apollo astronauts had a hard time answering the question, how fast are you moving? Speed away from Earth was one thing, and speed toward the moon was quite another. That's because the Earth and the moon move relative to one another. Of course, speed is a relative quantity. When Captain Kirk asks Lieutenant Sulu if the Starship Enterprise has reached a speed of warp 7, Sulu should reply, "Relative to what, Captain?" Such a sassy reply may get subordinate Starfleet officers in trouble, but it is the only good answer to the question, how fast are you moving? This is basic relativity talking, not fancy Einsteinian relativity, but good old-fashioned and still correct Galilean relativity. Galileo seems to have been the first person to realize that there is no such thing as an absolute speed. Speeds are relative. This means that speeds only have meaning when they are referred to a reference frame. Presumably, that reference frame is itself at rest. But then we have to ask again, at rest relative to what? Because even the concept of rest has lost any hint of absolute meaning. Speed is relative and rest is relative. Earth's speed is 19 miles per second relative to the Sun. The Enterprise's speed is warp 7 relative to the center of the Milky Way galaxy. Your speed is 0 relative to your easy chair. But depending on where you sit, it is hundreds of miles per hour relative to Earth's center. When we furrow a brow and ask, but how fast is Earth really moving? We imagine spaceship Earth plowing through the ocean of space as it orbits the Sun. But space is not an ocean. It has no substance as water does. Space is not a thing. Space is nothing. Space is no thing. You can move between 2 points in space, say between Earth and Mars, but you can't move through space. There's nothing to move through. It's like trying to say how much a hole weighs. A hole weighs exactly nothing, because a hole is nothing. It's a void, and so is space. To move relative to nothing is meaningless. The concepts of speed and of rest have only relative meaning. They are absolutely meaningless. They mean something only with respect to arbitrarily chosen, artificial frames of reference. If someday you are buckled into your spaceship and you see from the side window, say, a space station whiz by at constant speed, there is no way to know which of you is really moving. Neither of you is really moving because there is no deep reality about constant speed. Constant speed in a straight line has only relative meaning, a kind of relative reality. Does this mean that all motion is relative? No. Some motions have only relative meaning, but some motions have absolute meaning, are absolutely real. For example, constant speed is relative, but change in speed is absolute. Calling something absolute in science means that arbitrary standards are not used in its measurement. It is unambiguously measurable. When your spaceship fires its engines, your change in speed is beyond doubt. You feel it in your stomach, and your ship's sensors can measure it. Outside your window, the passing space station may seem to be changing speed, but the beings inside the station will not feel it, and no sensors can measure it. You are really changing speed, and they really are not. There's something absolutely real about changes in speed. The same goes for rotation. If your spaceship is spinning, you can feel it, and your ship's sensors can measure it. The space station outside may seem to be going around you, but it is you who feels queasy, not the folks in the space station. You are really spinning, and they really are not. There's something absolutely real about rotation. So some motions are relative, and some are not. There is no deep reality about constant speed, but changes in speed are deeply real, and so are rotations. We have to be thoughtful in our analysis of everyday experience in order to identify what is deeply real. Since we can be fooled by perceptions as basic as speed, maybe every perception deserves careful scrutiny. This is what inspired Einstein to his incredible insights about the speed of light and forward time travel. Knowing how to identify what is deeply real is tough and important work. If a police officer ever pulls you over for speeding and asks, "Do you know how fast you were going?" an insightful, though perhaps unwise, reply would be, "Relative to what?" And then, as you sit in the back seat of the police car and feel it accelerate toward jail, you can add, "But some things are absolute."
So I would not recommend asking a police officer that question if they pull you over, or responding that way rather. But again, whenever we define how fast we're going, when we talk about speed, it is always relative to something. In all of the discussions we've had so far about it, we've defined our frame of reference as just calling it 0 and assuming it's a stationary point on Earth because we're ignoring Earth's motion. But technically Earth is moving, and so if we took that into account, all of our speeds would be calculated a little bit differently. And so we're going to talk about what relative velocity, because we're not really going to use it with space, but with other examples of relative velocity where your frame of reference is moving and how that is going to cause the perceived speed of an object to be different than the actual speed relative to the ground. Okay, so again, if you want to write down some notes, it's not super lengthy today, but I do have a few slides to go through. So it mentions frame of reference or reference frame several times in the video, and I've said it as well. We define our frame of reference by choosing a reference point and describing the object's change in position compared to this point. So we've been saying our reference point is 0, whatever position of 0 is. With like your toy car RA, you were like, this is where we're going to measure from. You picked a point on the floor. It was arbitrary. It didn't really matter what point you picked. You could have still gathered the exact same data. But you chose a frame of reference. You chose a reference point. Okay. When you left home and drove to school today, you could say that you were moving with respect to your house. If I asked you how you got here, you could say, well, I drove away from my house. I went north or whatever. I went south, depending where you live. But you would be able to describe your motion with respect to your house. In that example, your initial position, your home, would be your reference point. Often you are the reference point. Whenever you describe the motion of the objects around you, you describe them with respect to your point of view. You could say, he was running away from me, or she came right at me, or whatever. But you would describe it with respect to your position. And so you would always describe things with respect to something. Okay, if I asked you for directions how to get, if I said, hey, how do I get to Walgreens? You would give me directions with an implied frame of reference as the school. You'd be like, we're starting here, and we're going to go in this direction this far. But we can only describe motion with respect to a reference point. When compared to the buildings, if you look at this image, when compared to the buildings along the road, the girl in the passenger seat is moving, because relative to those buildings, she's in motion. But if you compare her motion to the driver, this is just like the warm-up question, then you might say that she's stationary. It's the same thing as you next to your neighbor, except now the car in this warm-up was planet Earth in the warm-up. Okay, and so you have two people sitting in a moving object, or you have this room full of people sitting on a moving planet. Okay, but same thing, you look at your neighbor, they don't appear to be moving, but relative to the sun, they absolutely are. Okay, so again, it's always relative to some frame of reference, to some reference point. Relative velocity is how we describe our motion when our reference point is moving. Okay, so far we've only talked about velocities with an assumed standard of rest, an assumed stationary reference point on the ground. But if we now look at the fact that our reference point might be moving as well, now we can define our velocity with respect to that object, and we call that relative velocity. So relative velocity is the mathematical comparison of two or more objects' velocities. Here's a couple of example questions to think about. When you're driving down the road, how fast do the trees appear to move when you're sitting in a moving car? You're the one that's actually moving, but if you look out the window, the trees appear to be moving backwards with respect to you. And they appear to be moving backwards at whatever speed you're moving. They just look like they're going in the opposite direction. Or maybe this, how fast does your mom appear to move when you are sitting in the backseat of the car while she's driving? And again, that's like the warm-up question. She doesn't appear to be moving with respect to you, but you know that the car is actually moving, so with respect to the ground, she is moving, and so are you. This is a general rule to help you figure out how fast things are moving whenever your frame of reference is moving. So when you are moving, objects that approach you from the opposite direction will appear faster than their actual ground speed. So when you're on the road and there's a car coming the opposite direction and you pass one another, like in this animation up here, although this person's going the wrong way on the road, but they're going to appear to be moving faster than you are. Whenever you actually pass those cars, it seems like really quick, especially on the highway. It's like, and you can sometimes hear that sound too. Okay, but they're going to appear faster than they're actually going to you, because your speed and theirs are taken into account whenever you're looking at how fast they appear to be moving. Objects that pass you going the same direction appear slower than their actual ground speed, again, from your frame of reference. If you're driving on the freeway going 70 and somebody's speeding and they're going 85, they're going to pass you, but they only look like they're moving 15 miles an hour faster than you are in that example. They don't actually look like, with respect to you, that they're moving 85. Now you might be like, that guy's driving really fast, because you already know that you're moving. Okay, but relative to your position, they would appear slower than their actual ground speed. So there's an equation that helps us calculate our relative velocities, and you might want to jot this down. Actually, it's on the next slide, sorry. One more thing. If you are moving and you pass an object, that object will appear to move backwards with respect to you. Think of the trees on the roadside. As you're driving, the trees appear to be going backwards. Or if you look at this animation, pretend you're in this red car. If you look out your window, these other cars, as you pass them, are going to appear to be moving backwards with respect to you. They're also going to appear slower than their actual speed. Here's the equation I was talking about. Relative velocity is equal to the velocity of the object minus the velocity of the observer. So one of the objects is the observer. Typically that's you whenever you're talking about your motion with respect to other things. And so from your point of view, the object's velocity will appear different, and that's this relative velocity over here. Okay, so if you look at this example question, and again you might want to write down a couple of these examples. It says you're driving east at 50 miles per hour when a wrong way car comes at you 40 miles per hour to the west. How fast does the wrong way driver appear to move from your frame of reference? Okay, so if you're trying to find relative velocity, we're going to plug into this equation. Again, you are going to be the observer. Okay, the other wrong way car is going to be the object. The fact that you're moving opposite directions is going to matter when you use this equation. We're going to say that things moving to the east are positive and things moving to the west are negative, just like the coordinate system in math. Things to the right are positive, things to the left are negative. You have to keep the signs on the numbers for this equation to work. So if I plug into this equation, I would plug in like this. The object is moving negative 40 because it's 40 to the west. I am moving positive 50 because I am 50 to the east. And so when I plug in this negative 40 minus positive 50, I have this, negative 40 minus 50, which gives me a relative velocity of negative 90 miles per hour, which means that they would be moving 90 miles per hour to the west. Again, the negative sign just tells us which direction they're going. And you do need a direction with relative velocity because velocity is still a vector. Okay, any questions about the example? I've got a couple more. Okay, so you can jot down any of these. I am on slide 168. If I go too fast, you're welcome to open it up on your own screen. Okay, but again, you're plugging into the equation, but before you plug in, you have to check your signs. You need to make sure you define one direction as positive and one as negative. By convention, we typically consider east and north to be positive, and we consider west and south to be negative. All right, let's try this one. You are driving on a track at 125 miles per hour and a black car passes you at 140 miles per hour. How fast is that car moving from your perspective? I gave you a general rule. That general rule said if somebody passes you going the same direction, they're going to appear slower than their actual speed. So this car is going to look like it's moving slower than 140. If we plug into the equation, we're going to see that as well. Velocity, relative velocity equals the velocity of our object minus the velocity of our observer. It doesn't give us a direction here, but you're going the same direction, so let's just call them both positive. You could call them both negative if you want. I don't know why you would do that, but positive's easier. So object is the car passing us at 140. We are going 125, so 140 minus 125 means that this car appears to be traveling 15 miles per hour forward past us, or 15 miles per hour faster than you. Again, that little general rule said if you're going the same direction, they appear slower than their actual speed, and that is obviously slower than 140 because it's just the difference in your speeds. All right, let's look at another one. You are driving north in a red car at 50 miles per hour as you pass a blue car that is also traveling north at 30 miles per hour. How fast does the blue car appear to move from your perspective? Okay, again, same equation. You're both going the same direction. We're going to call north positive. The object is the blue car that's going 30. We are the red car going 50. 30 minus 50 is a negative number. And that is because when you pass something, that other object appears to be moving backwards from your perspective. Okay, so that car would appear to be moving 20 miles per hour backwards, or in this case, south, since we used north. Any questions? about this. The equation itself is pretty straightforward, okay? So you should be able to plug into it, just check your signs, especially if they're going opposite directions. All right, let's try another one, and this is similar to what you're going to see in your assignment today. It says, if you are riding in this boat, what is the apparent velocity of each from your frame of reference? So if you're in the boat is moving 12 meters per second to the west. How fast does this bird appear to be moving? How fast does this person appear to be moving? And how fast does this car appear to be moving? I would like you guys to take a look at this, maybe even turn and talk to your neighbor if you're not sure. I'm going to set a timer for 27 seconds, and then I'm going to call on some of you guys to share what you think the answer to each of these is. So discuss with your neighbors, please. It is possible to answer these without using an equation. You can also just logic your way through it. All right, let's do the bird first. Okay, so how fast does the bird appear to be moving? Let's see, Ife. Okay, which direction? Yep, 5 meters per second to the west. Okay, the bird would be look like it's moving 5 meters per second faster than you are in the same direction. You're going west, so the bird looks like it's going west as well. Okay, what about the person that's down here? How fast does that person appear to move, Addison? Yeah, 12 meters per second, which way? East. They're not moving at all, but when you pass them, they're going to look like they are. That's kind of like the trees out your window while you're driving. Thank you, Addison. And then the car is the last one. What do you think, Taylor?
12 east.
Okay, so the boat is going 12 west. The car is going 32 meters per second east. So let's start with this. Is it going to look like it's faster or slower than it's actually moving? Faster, because they're going opposite. That's that rule. So that should probably help you figure out what to do here. Okay, so if it's going 12 west and the car is going 32 east, how fast does the car look? Yeah, you're going to add them. Okay, you're really subtracting a negative, but 44 which way? East. Okay, does that make sense? All right, what if I did this? Now I said you're still in this boat, but now the boat's moving and the river's moving. Okay, there's a current, 3 meters per second. Okay, then how fast is the boat moving relative to the ground now?
9 meters per second.
Yeah, so you'd have to subtract that out, and then you'd have to redo all of the questions again, okay, if I had asked you to do that. The reason I put that in there is because I do ask you to do that on some of the ones, not with the river specifically, but some of the ones where you're on a thing that's also moving on another thing, and anyway. So you'll see it whenever you get to it, but there is one in there. So if you would, please go ahead and head to My Open Math. You were looking for the assignment 111, Relative Velocity Problem Set. You have the remainder of the class period to work on it, which means that you guys have about 25 minutes, which should be plenty of time to finish the entire thing, I think. But if for some reason you don't finish it in here, it will be homework for you. So obviously, I would recommend that you get as much of it done as possible while you're in the room. That way you have people to work with and to ask questions of if you're not sure about how to do it. The thing has, I'm trying to see how many questions it has because I can't remember. It only has 10 questions on it, so it's not very lengthy. If you finish this early, which a lot of you probably will, then I would recommend that you work on the unit summary. Again, the unit summary is a review for the entire unit, and it will get you ready for your quiz tomorrow and your test on Thursday. The only thing that's not in the unit summary is the stuff you're doing right now. Relative velocity is not in that document. So please make sure that you look at this in addition to the unit summary as you are studying for your quiz and for your test. All right, if you guys have questions as you're working, please let me know.